Can you hear me? Okay, yeah. So good morning, everyone. First of all, thanks to Natasha and Sergei for the opportunity of being here to show our work. And I'd like to mention that all the work has been done here, which I will present, has been done at the Quantum Matter Institute in Vancouver, UBC, but also it's part of the effort of the International Max Planck Center we have in Vancouver, which in fact is the Max Planck UBC University of Tokyo Center for Quantum Materials, bringing together the three universities. Topic of the talk is condensate, in particular superconducting or excitonic. I'll start though with a very quick introduction about time-resolved photon emission, in particular focusing on the importance of development of extreme UV lasers for this particular work. I'll then move on to the cuprates, looking at coherence in a superconducting condensate, but also a quick look at a pseudogap type behavior. And finally, I'll move on to the possible excitonic insulator, tantalum, nickel, selenium, and so now looking at different kind of condensate. And one key question I like to highlight here is photon emission is a single particle spectroscopy, does not directly probe condensate coherence, and so you're going to see that we try to look at that and get to that quantity through a detailed analysis of the spectral function. And towards the end, I'll show you what are the future prospects for these kind of studies. Let me start with introduction, and I'd like to highlight that the work we have done at UBC and we're doing at UBC is part of a more than 10 years effort between two groups, my own group and David Jones' group, shown here. So we have come together, spectroscopy and laser developments, to set up a lab where you could do angle-resolved photon emission with lasers in a time-resolved fashion. So here is an infrared pulse coming in onto our samples and a UV pulse that we use to probe the excitations in the sample. The key, of course, as you've already seen, is the generation of photons, high enough energy photons that you can probe the entire Brillouin zone of your material. So we're looking at more than 10 electron volts photon energy. And when you do that, you have to use a gas jet. And that's where the challenge comes in. I'd like to also mention some of the group members, in particular some of the students and postdocs now have moved on. Marta Zonno is actually a beamline scientist at the Soleil synchrotron in the Cassiopeia beamline, Fabio Boschini, now a faculty member in Montreal, and Katie now a postdoc in Alexei Kimmel's group in the Netherlands. Just one slide about the laser. So usually we want to go to high photon energy. We use a gas jet, and the challenge is you need very strongly amplified pulses, so that means low repetition rates. You also have to have very short pulses, so compression, which immediately also means low energy resolution. And so we wanted to get beyond that to really get the best of the two, so high energy and temporal resolutions. So the idea was to put a cavity around the gas jet, and now we have a repetition rate which is defined by the path, the period around this cavity. So in fact, we work at 60 megahertz. The cavity is 5 meters long with many bounces, and so now we are all of a sudden in a very high repetition rate regime. What it means now also, we don't need to amplify, we don't need to compress the pulses, so very low peak powers, but many photons per second. Here you see some snapshots of the different harmonics you can get with different gases, argon or krypton, and so you can go all the way up to more than 40 electron volts this way. The key, of course, as I said, is energy versus time resolution. Here you see a nice collection of results in a review paper from ZX Shen's group, and you see that the limit is basically the Gaussian limit, where basically set by Heisenberg, how much can you push one versus the other. And when you go to high photon energy, so for instance in green here, 20 to 30 electron volts, you see that it's much easier to achieve the limit if you're really pushing down the time. So you're making your pulses very compressed, but now you lose the energy resolution. And so that's where we are. This is our data point. So we really try to go for this sweet spot where you have a few hundred femtosecond and few tens of MeV resolution. So in practice, it's going to be 15 MeV resolution in energy and about 150 in time. And why is that important? I'll just give one slide on that. Here is, yesterday we've seen experiment on graphite. Here is a graphene, sorry. Here is a case that we have done on graphite, but I use graphene as an example. Here you have your Dirac cone. You come in, you pump your system, you excite electrons into the unoccupied side of the electronic structure. And now there are two mechanisms that can happen. One is electron scattering, so the electron relax back down, or electron funnel scattering, and electrons will relax back down to an energy which is dictated by a particular phonon. Now, you can use now, working in the time domain, this approach to really extract the electron-phonon coupling or the electron-phonon matrix elements. And what happens? Well, here is a simulation done by Tom Devereux's group at Stanford. Basically, you start off with an occupied state. You pump up into the unoccupied part of a Dirac cone. You have now two states you can see. But after a characteristic time, T q, the electron-phonon scattering time, you start seeing intensity coming down and trickling down along the cone in discrete steps defined by the energy of the phonon itself. And so this is the beauty of this simple relation. If you have a resolution to see these features, you can extract directly the T q, so the tau q, so the electron-phonon scattering time, and immediately you can get either the electron-phonon matrix element for a given q or the electron-phonon coupling as you wish. So experimentally, this is shown here. Instead of the angle resolved map, I'm showing an angle integrated spectrum of a feature like this. And here you see the actual raw data. You see there is a background. This is the electron-electron scattering. But on top of the background, there is some structure. If we subtract the background, now the structure is 3 peaks in this case. 2 of them are optically allowed transitions. So these are really transition between valence and conduction bands. But then there is a feature which is not an optically allowed transition. It's separated in energy exactly by the energy of a K phonon for the system. And so now you just watch, over time, by doing a pump and probe experiment, how the intensity transfer from this main peak to the phonon replica into the spectrum. And you can see that very clearly. You do as a function of delay your experiment. And now if you have, in addition to the energy resolution to resolve the structure, you also have a temporal resolution. You can see that 2 of these transitions in blue, the optical ones, are peaking at 0 delay. That's when you have the highest probability of pumping into those unoccupied states. The phonon replica in red here comes up with a delay of about 50 femtosecond. And so that is the time that it takes for the electron to now scatter with the phonon and populate the state here. And so immediately you can get, from a measurement, a value for the electron-phonon matrix element, so really the projected matrix element, and compare that to DFT calculation here done by Lex Kemper. So that's really the beauty of having the enough energy and time resolution and working then in the time domain to extract these microscopic quantities. Let me now move to, actually just one point I'd like to make before I move to the case of the cuprates is if you look at the evolution, of the effort in time resolved spectroscopy over time, and in particular using photoemission, the early 90s is when the 2-dimensional detectors have been developed where you can simultaneously acquire energy versus momentum. So you take this snapshot of a band dispersion. This is really when angle resolved photoemission became a mature technique. And then over the years, we have seen this very large increase of time resolved work. And really that has to be ascribed to the development of laser system, either in crystals, so limited to below 10 electron volts, or with high harmonic generation in gases. And really that has made this technique available for all possible materials. And this is now nicely being reviewed by Marta and Fabio in a paper we just published recently this year. And thanks to many of you who have contributed with materials and comments for this work. Let me now move to the case of the cuprates. And so first I'll start off with the superconducting condensate. And in fact, I'd like to start off with the most elegant way of describing the phase diagram of cuprates. Temperature versus doping, and here is a dome where you find superconductivity, and here's the idea going back to Emery and Kibelson, where you have that the dome, and one way to understand the dome is that one side of it is defined by the pairing, so the energy scale of the pairing, and the other side by phase coherence. And so phase coherence dominating or being the limiting factor in the underdoped side and pairing on the overdoped side. And the question is, can we use time resolved approaches to really look at coherence versus pairing independently, and so really basically play around with phase fluctuations in this particular system. And so how can we do that? And that's where we come to then try to measure coherence in such system. So here we're going to make use of a spectral function. Spectral function basically defines and describes a single particle excitation in a system. If you have a simple metal, there's going to be a dispersion defined by the poles, so the location of the basically energy and momentum states, and a lifetime. Of course, correlation will change both, and so the imaginary part of the self-energy is there a normalization of a characteristic energy, and the real part, and the imaginary part is the lifetime of those excitations. But now if you go to a superconductor, you also have to put in something that describes the superconducting state, and here it is. So now the self-energy acquires terms, which is defined by delta, the pairing, so the gap, and a gamma p, which is a pair-breaking scattering rate. This, I want to make clear, is a very phenomenological spectral function, was done by Norman or Franz and Millis, used by many people. Is it a phenomenological way of describing the data? And what would it look like? Well, if we look in a region where we have a superconducting gap, here is the chemical potential, and we are below Tc. Now we find two peaks in the spectral function, one below and one above the chemical potential, and the difference between the two of them is 2 delta, the superconducting pairing. And now the question is, if phase coherence, if we go and pump the system, and now we can tell the difference whether or not delta or gamma are dominating the effect. If we go and pump the system and quench superconductivity, and we observe, for instance, that the gap gets smaller, then we know that by quenching superconductivity, or by pumping the system, we are quenching superconductivity through a reduction of the gap. If, however, we see that the peaks remain about the same position, and in fact they get broader, and spectral weight fills in the gap, then we know that we're quenching superconductivity by manipulating the gamma p, the pair-breaking scattering rate. So the idea is to do an experiment where we pump the system and see where the action is. Is the gap closing or is it filling? And we do it dynamically, and we use that as a way to define where much of the action is either in the delta or in the gamma p. And yes,
So gamma p is the pair-breaking.
Pair-breaking.
Gamma s?
Gamma s is a single particle scattering rate, which is also there. However, below, a low temperature won't play much of a role, so that is not going to be changing. But is also there in the system. Is also there. So when you do an analysis of a spectral function, you would start off with an analysis above Tc, which allows you to define the gamma s, and then you go below Tc, and now what we can show is that much of the action is in the gamma p. And in fact, even the work done by Luca and others show that once you're below Tc, much of the action, so once you go below into the superconducting state, much of the action is in the gamma p.
Is one of them elastic and other inelastic?
Well, I would say both of them in this case have an inelastic component. I would say both of them can have an inelastic component. It's just one is really for the single particle, the other one is for the Cooper pairs. Right? So one single particle, Cooper pairs. And again, I like to link the gamma p, of course, to phase fluctuation. If you have, the point I want to make is that if you have phase fluctuation, of course, you're going to see an action in the gamma p. Now, if you see an action in the gamma p, I like to make the connection to phase fluctuations being important. So let me now go to the experiment, having in mind these two scenarios, the closing of a gap or the filling of a gap. And here is the work that Fabio has done now. You take a underdoped bismuth cuprates, and you start at low temperature, no pump, and you see a nice peak structure above and below the gap. I just remind you that photo emission measures only the occupied part of the spectral function, but if you have enough statistics and you divide off Fermi function and resolution effects, then you can see a nice particle-hole symmetric gap and a particle-hole symmetric peaks across this gap. Now you start pumping the system, and immediately, visually, you can see that the peaks are dropping in height, they're getting broader, there is no much of a shift in the gap position, the gap is not quite closing, but you do filling the gap. And so immediately you could conclude that the gap is not closing, it's filling in. You can do a much more detailed analysis if you now use the spectral function, and you do a fate of your spectra as a function of all delays that we have. And then we can plot in black the reduction of the gap, and you can see it's about a 10% reduction of the gap itself. Much of the action, as you can see visually, is in the gamma p, so the broadening of the spectral function in the superconducting state as you quench superconductivity. Now, this has been done, again, Luke has done much work in that direction, also using equilibrium photo emission. I'd like to stress how this is now done time resolved and is not a thermal effect. And so I'd like to first start off with a cartoon. What is actually happening here? You have a condensate, you come in, you're pumping the system, you're creating hot quasi-particles. Those hot quasi-particles really are removed from the condensate, but that doesn't reduce the phase coherence of the condensate. You're just removing quasi-particles. However, they have to thermalize. And as they thermalize, they do by emitting, creating a population of non-thermal bosons. And these non-thermal bosons are the ones which are responsible for fluctuations of the phase of the condensate, and so the loss of condensate. Now, and I want to stress that this is not thermal in a sense that, of course, we are creating hot quasi-particles. We see that, the temperature of the system, electronic, goes up to above 60 Kelvin or so. That corresponds to a reduction of the gap itself. Now, we can, on this plot, as a function of delay, we can plot in black the data from before, so it's basically the fit to the data from before for the gap itself, but reversed, and in blue, the lifetime effects, so the gamma p, so the pair breaking scattering rate. So here for the gap, the gap is decreasing by an effective 10%. Here I'm just plotting the data normalized from 0 to 1 and reverse so that you can compare them to the green data points. The green data points is the intensity measured here above the chemical potential. What you see here is a map of pump on the sample minus no pump, and so you have an increase of population above the chemical potential, a depletion of population, and so this increase of population tells you about the electronic temperature of the system. And you can see how the evolution in time of the pairing and of the temperature, the electronic temperature, go hand in hand. However, the gamma p is really separate, sets up with a delay of about 500 femtosecond, which is the time needed to create the non-thermal bosons. So it really is a different behavior. So it's a non-thermal behavior, and yet the gamma p tells us the phase fluctuation are really playing a key role in this particular case. So even though we don't have direct access to phase coherence of the condensate, we can see the evolution of that through the evolution of a spectral function and the different terms in the spectral function. Let me now move to another case, which is still cuprates, but now the pseudo-gap phase. And I'll do that on electron-doped cuprates. So this is neodymium, cerium, copper oxide. The difference between the whole dope is that you have a very strong antiferrometric phase on one side, then you have superconductivity. And the question is, we have, even here at optimal doping, we still have a pseudo-gap. You can see it if you look at the Fermi surface. And instead of a continuous evolution, continuous spectral weight along the Fermi surface, you have a suppression of spectral weight there where the Fermi surface crosses the antiferrometric zone boundary. And the question is, what is the source of this suppression? What is the source of the loss of intensity, that pseudo-gap, given that the system is not in the antiferrometric state? So at best, you would have very short-range antiferrometric correlation. Is that so? Is that the origin of that pseudo-gap? So experimentally, we can look at that again, and here you have your Fermi surface at the node, and so we're going to compare now data taken along the nodes and take data taken at the location of the pseudo-gap itself. In this case, we use the laser similar to what Luca was mentioning before, not just to do a non-thermal effect, but actually to transfer enough energy to the sample to increase the electronic temperature of the sample. And so what we do is we can look at the data along the nodal direction, and we can basically extract a Fermi-Dirac distribution from where the gap is actually zero. Both the superconducting and pseudo-gap are zero here. We can extract a Fermi-Dirac distribution for different delays and different pump fluencies. So now each of these curves will correspond to a different electronic temperature. You can see that going up, the Fermi edge gets broadened out. It's a higher electronic temperature. So effectively, we can plot, as a function of delay, the electronic temperature for different fluencies of the system. So you excite the system. When the electrons go up, gets excited, then they get thermalized. Eventually, initially, of course, you have a regime where there is no thermalization yet, but eventually they thermalize and they define a proper electronic temperature through a Fermi-Dirac distribution. Next, we're going to look at the intensity in this region, and we're going to plot the intensity in that region as a function of electronic temperature. And so this is the outcome. So here we have the intensity of the pseudo-gap. As we increase the electronic temperature, we see that the intensity at the hot spots, so-called, increases and eventually saturates. And now it's interesting to see where does that happen? Well, the saturation happens to at a temperature which is actually T star for this particular system. It's a crossover, clearly. Also, the temperature dependence seems to follow here the green line, and the green line is 1 over the spin correlation length. And so one can conclude from this a few important points. First of all is T star takes place when the spin correlation length, we have no long range order, and the spin correlation length now is less than 10 to 15 lattice sites. So that's when this takes place. We can also fit, as we did before, the spectral function using, or the photoemission intensity using now a spectral function or a Green's function, which instead of a superconducting gap has a terms which refers to spin fluctuation. This is the gamma now. And delta is now not a superconducting gap, but a pseudo gap. So we can do pretty much the same job as before. And what we see is that we can reproduce the spectral function well when we actually, keep the pseudo gap value constant, and much of the action is instead in the lifetime. Once again. So once again, the lifetime is the key feature. And in fact, we see that the saturation here happens when the lifetime, the gamma, as a function of T star, has become of the order of 2 times the pseudo gap value. So it's of a value psi. So the conclusion is that the pseudo gap is actually not closing pretty much as the superconducting gap, but is also filling in. And so that pseudo gap energy state survives, and all of the action is in the lifetime of the excitation. And finally, this is really directly an evidence that the pseudo gap is coming from short-range spin correlation in the electron-doped cuprate. So now we have 2 systems for both of which the action is a lifetime, the energy scale stays the same, and this provides us a view on the coherence of those particular condensates. Of course, the superconducting condensate is a bona fide type condensate. The pseudo gap is still a particular state to be defined.
When you say spin correlations, do you mean antiferromagnetic?
Yes, yes, and this is actually from neutron. So the green curve here is neutron work from Martin Graven. So neutron scattering, and you can see how the spin-spin correlation changes the functional temperature. Yeah. Thanks for the question. I forgot to mention that. In the last couple of minutes, I'd like to move to the so-called or potential excitonic condensate or insulator tantalum nickel selenium. I'll be very quick on the introduction, but basically the idea is that where you start from a semi-metal or a semiconductor, if you have a strong particle-hole pairing, you may end up through a BC type mechanism or BCS type mechanism in what is called an excitonic insulator and have an excitonic condensate. As far as dispersion and featured is, a typical aspect is the creation of a gap, but more so the M-shape functional form of that valence band. And so the gap has been nicely seen by STM and other techniques. The M-shaped dispersion has been seen by photo emission. Now the challenge is that the electronic phase transition about around room temperature is happening concomitant with the structural phase transition. So whether electronic or structural, this is still a question for the system. There has been nice time resolved ARPES work by a number of groups, and here you have, if you compare these 2 results, one is in favor of a gap closure due to the photodoping, suggesting that the transition is electronic in nature. The other one is in favor of a robust gap, suggesting the transition is structural. One key thing to keep an eye on here is the fluencies used for the pump, 1.5 millijoule, and half of the fluence here. So certainly there is a fluence dependence, which is important. In any case, the question is still open. Is the gap of electronic or structural nature? And so that's where we come in. And what we do here, we look at our photoemission intensity before the pump comes in, so negative delays, and then after the pump has come in. Then here, we're just plotting the data from the gamma point, a single spectrum. And what you can see, comparing the no pump with pump, is again a small shift of a peak position. So small change of gaps, but big change in the width. So basically, the change in the width is a factor of 10 bigger than the shift in peak position. So once again, the action appears to be in the lifetime of a system. I can go through the detail here, please ask me, but this is the message. The lifetime is what really changes here. So now we have teamed up with people in Flatiron, in particular Andy Millis, Dennis Golesh, and we have looked at how can we model the system. So here we look at the evolution of the width as a function of photodoping, so fluence. And what we can see is the experimental data up here, big increase with fluence, and then we try to reproduce it with a model where either we include electron phonon scattering or electron scattering. And we can see that with the phonons, so when the phonons are dominating, we are not able to come up here. In order to come up here, we really need the electron scattering to be dominating in the system. So we can still not conclude that the transition is excitonic-like, but we can see that the electrons are really playing a key role. And in the last 2 minutes, I'd like to say that we have then pushed the system to see if we can work on exfoliated, the exfoliated version of this system. We have developed a micro ARPES system where we can go down to 10 microns and then exfoliate the materials in situ. So now I'm going to show you work that was done with a 10 micron spot on a flake of the same material done in situ. And here is what you see. So what this is a map of TNS exfoliated in situ on gold 111, and we do a scan here over this trace. White means higher intensity, so thicker material. In black, you have basically the monolayer, and here is evolution of the spectra. So as you go down, you go from a well-defined valence band with a gap, about a 300 MeV gap, as in the bulk. But as you go thinner and thinner and you reach the monolayer, all of a sudden the system becomes metallic. And so you're basically quenching that insulating state. And you're basically doing that through gating, through surface gating onto the gold surface. So that really suggests very strongly that it's just enough to change the electronic content and the screening in particular to quench that state, suggesting that the nature of this state may be electronic in origin, so potentially an excitonic condensate. Similarly, we have done now a pump and probe experiment, but not on a flake, but on a thick crystals, but now using a photon energy from the pump, which is resonating with the gap itself, 300 MeV, just exactly at the gap. And what we see here is in a different spectra, so pump, no pump. Blue is depletion of population, red is increase of population. We see that as we increase the fluence, we're still very small fluences compared to the 1.6 or so millijoule that I showed you before. You go from an insulating state all the way back to a metallic state, which is pretty much the same as this one done through surface gating. So we have two ways of quenching the condensate electronically through light doping, through the surface gating, or through very delicate pumping resonating with a gap. And in both cases, we produce we are back to a metallic phase. So this is really suggesting that the ground state at low temperature would be an excitonic type. And if you're interested, I can discuss whether BCS or BC. With this, I like to just mention that, of course, the problem with this is angular result formation only measures single particle. You may have a condensate, Cooper pairs, and so on, but you only remove one particle here, so you lose information about the many-body wave function left behind. And what we're developing now is what is called a 2E ARPES system, where we come in at high enough energy photons, 50 V, to remove simultaneously 2 electrons, detect them simultaneously in coincidence, and this way be able to really infer what is the total momentum of a Cooper pair and what is the inner structure of a Cooper pair. With this, I come to my conclusions. I like to mention, all the people who contributed on the bismuth cuprates and electron doped cuprates, both in terms of the sample, the neutron scattering, the time resolved optics, and when it comes to the excitonic insulators, all the people from Flatiron, and as well as collaborators from Germany and Max Planck Society. And last word, this was the past, but of course there is a lot of developments going on in these techniques, so I really think that the future for time resolved photon emission is really bright, and especially when it comes to pair correlation type spectroscopy like the last one I was just describing. Thank you so much.